Okay, in this video, we're going to be looking at how to use permutations and combinations in probability. And what we'll look at is permutations of unlike objects, permutations that involve like objects, and combinations. Let's start off with permutations of unlike objects. We first need to define what a permutation is. It is an arrangement of things in a definite order with no repetitions. Okay, so here the order is going to be very important and there is no repetition. So here, that's what a permutation is. Okay, also we'll look at fundamental counting principle. Is this: if an event M occurs in M ways, and after M has occurred, event N can occur in N ways, then event M followed by event N can occur in M times N ways. So you'll multiply the number of ways that M occurs times the number of ways that N occurs. That's the basic fundamental counting principle. Also, definition is this: n factorial. And we denote that with an n with an exclamation mark. Okay? That's going to be the product of decreasing integers from the number that's given to you, and you're going to decrease it by 1, and then you're going to multiply it. So in this case, in this notation, it'll be n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1. So in this case here, if I have, let's say, 7 factorial, which is going to be 7 with an exclamation mark, the way I would expand that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And then I'll multiply those integers out completely. And I also need to mention, since I'm on the subject of n factorial, by definition, 0 factorial is always going to be equal to 1. Okay, so I do need to mention that 0 factorial is always going to be equal to 1 by definition. Okay, let's look at permutations of objects in a set. The number of permutations of R objects chosen from a set of N objects where R is going to be some number that's bigger than or equal to 0 and less than or equal to N is denoted by NPR and is given by this. NPR is going to be n factorial divided by n minus r factorial. And those n minus r is in parentheses. And it's going to be factorial. Okay, so if we want to look at a couple of examples using permutations and the fundamental counting principle, it would be this. In part A, a baseball team has 9 players. Find the number of ways the manager can arrange the batting order. Okay, so here we start off with 9, and then we start using the product of descending integers. So it'll be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Multiply that out completely, you'll get 362,880. So here, there are 362,880 ways that the baseball manager can arrange the batting order of a baseball team with 9 players. Okay. Now in part B, you want to find the number of ways of choosing 3 initials from the alphabet if none of the letters can be repeated. Here, there are no repetitions, so that means we have to use a permutation type problem here. So we set this up as 26P3. Your N is 26 and R is going to be 3. Okay, so here we use that formula. And I'll go ahead and rewrite that. Where you have NPR, that's going to be n factorial, divided by the quantity n minus r factorial. In this case, our n was 26, so that's going to be 26 factorial divided by 26 minus 3 factorial. Now 26 minus 3, that's going to be 23. So now you have 26 factorial divided by 23 factorial. Now notice they expanded 26 factorial as 26 times 25 times 24 times 23, and they stopped at 23 factorial because notice in the denominator you have 23 factorial, which means the 23 factorials divide out. So all you have to do this, multiply 26 times 25 times 24, you'll get 15,600. So there are 15,600 ways of choosing three initials from the alphabet if none of those letters can be repeated. All right, next we'll look at permutations that involve like objects. If there are n objects of which r are alike, R1 and R like, R2 are alike, and so on through R sub k, then the number of different arrangements of all n objects where alike objects are indistinguishable is going to be equal to this. You have n factorial, and all that's going to be divided by the product of R1 factorial, R2 factorial, R3 factorial, and so on all the way up to R sub k factorial. Like in this situation here, find the number of rearrangements of the letters in each of the following words. In part A, you got bubble. Now notice in the word bubble there are three letters. There are three B's in the word bubble. And there's 6 letters altogether, so that means the numerator is 6 factorial. That's going to be divided by, now notice that there are only 3 B's in the word bubble, so that means in our denominator we need 3 factorial here. 6 factorial can be expanded as 6 times 5 times 4 times 3 factorial, which will stop there because already in the denominator we have 3 factorial. So that means that 3 factorials can be divided out completely. So now you're just left with 6 times 5 times 4, which is 120. So there are 120 rearrangements of the letters in the word bubble. Now part B, the word statistics. So let's find the number of rearrangements of the letters in that word. There are 10 letters in the word statistics, so the numerator is 10 factorial. Notice that there are 1, 2, 3 S's in statistics, so you have a 3 factorial. You also have 3 T's in the word statistics, that's another 3 factorial. And 2 I's in the word statistics, that's 2 factorial. Now notice we expanded the 10 factorial all the way out completely. And the same thing with this 3 factorial, this other 3 factorial, and then 2 factorial. Okay, so here we can, of course, divide out some numbers here, like the 3, the 2, and a 1. And I know this 2 times this 2 would be 4, so that means this 2, those 2's in the bottom, in the denominator, can be divided out with a 4. And then also I see that 3 is divisible by, can go into 6 2 times. And then you can just say 10 times 9 times 8 times 7 times 2 times 5. You'll end up with 50,400. So there are 50,400 rearrangements of the letters in the word statistics. All right, next we'll look at combinations. A combination is an arrangement of things in which the order makes no difference. So here, if the order is not important, then that means that the problem that we're dealing with is a combination type problem. And to find the number of combinations possible in a counting problem, we find the number of permutations and then divide by the number of ways in which each choice can be arranged. So now, in CR, N is the number that's given to us, or the number of items that's given to us, and R is the number of items that we're choosing from N. That's going to end up being this, N factorial divided by r factorial divided by times the quantity n minus r factorial. That's this formula right here. Now we're going to look at how this formula can be used in some of these examples, like example 9-18. The Library of Science Book Club offers three free books from a list of 12. If you circle 3 choices from a list of 42 numbers representing the book on a postcard, how many possible choices are there? In this case, your order is not going to be important, so that means you have a combination problem, which means you have 42 times 41 times 40. Okay? And that product represents the number of ways to choose the free book. So if you multiply the 42 times 41 times 40, that will give you 68,880 ways to choose those free books. And the 3 circle numbers can be arranged in 6 ways. That's 3 times 2 times 1. So in this case here, using that particular formula, NCR, that's 42C3, by the way. Your N is 42, so it's B42 factorial. R is 3, so it's 3 factorial. That's multiplied by N minus R, which is 42 minus 3. That quantity is going to be factorial. So in this case here, 42 minus 3 is going to be 39. So you have 42 factorial divided by 3 factorial times 39 factorial. Now what we can do here is expand 42 factorial as 42 times 41 times 40 times 39 factorial. Now the 3 factorial, we'll go ahead and expand that as 3 times 2 times 1. And the 39 factorial, I'll just leave as is, because I can divide out the 39 factorials. Now, if I multiply 3 times 2 times 1, that's 6. I know the 6 can go into 42 7 times. So all I have to do here is multiply 7 times 41 times 40 to get 11,480. So in this case, there are 11,480 possible choices. So in this case here, order is not important, so we use combinations. If order is important, then we use permutation. Another example would be this. At the beginning of the second quarter of a mathematics class for elementary school teachers, each of the class's 25 students shook hands with each of the other students exactly once. How many handshakes took place? Since the handshake took place between A and B, and it's the same as that between persons B and A, this problem of choosing combinations of 25 people 2 at a time. So that's why it's NCR, which is 25 factorial divided by 2 factorial times the quantity 25 minus 2 factorial, which would be 25 factorial divided by 2 factorial times 25 minus 2 factorial. 25 minus 2 is 23, so you have 23 factorial. Expand that 25 factorial to 25 times 24 times 23 factorial. You can divide out the 23 factorial. So now 25 times 24 divided by 2 will give you 300. So there were 300 handshakes that took place. Another example would be, given a class of 12 girls and 10 boys, answer each of the following. In part A, how many ways can a committee of 5 consisting of 3 girls and 2 boys be chosen? Here, order is not important here in this case, so we use combinations here. So for the girls, they can be chosen this many ways, 12C3. And for boys, it's 10C2, because we're choosing 2 boys out of 10 boys. And we're choosing 3 girls out of 10. Now, by using a fundamental counting principle, the total number of committees would be this. If we say 12C3 is going to be this. 12 factorial divided by 3 factorial times 12 minus 3 factorial, which means you're going to have 12 factorial divided by 3 factorial times 9 factorial. And that represents this right here. As you expand 12 factorial is 12 times 11 times 10 times 9 factorial, but the 9 factorials divide out, so you're only left with a 3 factorial in the denominator. And then for the 10C2, that's this. 10 factorial divided by 2 factorial times 10 minus 2 factorial. So in this case here, you have 10 factorial divided by 2 factorial times 8 factorial. But if you expand 10 factorial to 10 times 9 times 8 factorial, we can divide out the 8 factorial. You're going to be left with just this right here. 10 times 9 divided by 2. Okay. Now, if you simplify that, you'll end up with 9,900. So in this case here, there are 9,900 ways that a committee of 5, consisting of 3 girls and 2 boys, can be chosen. Okay, part B, what's the probability that a committee of 5 chosen at random from the class consists of 3 girls and 2 boys? Okay. All right, the total number of committees of 5 would be 22C5, which was in this case 26,334 if you were to use the formula. Now from part A, we know that there are 9,900 ways to choose 3 girls and 2 boys. So here, that probability would be 9,900 divided by 26,334, and as a decimal, you'll get 0.3759. So the probability that a committee of 5 chosen at random from a class consists of 3 girls and 2 boys would be 0.3759. And then part C was the probability that a committee of 5 chosen at random from a class has no boys. Okay, so the total number of ways to choose 5 girls and no boys from 12 girls in a class would be this. 10C0. Okay. Now in this case here, of course, you have 10 factorial times, to get this, you have 10 factorial times 0 factorial times 10 minus 0, and that quantity is factorial. In this case here, you got 10 factorial. 0 factorial by definition is 1. 10 minus 0 is 10, so that's 10 factorial. Divide that out, you're going to get the 1. That's where this 1 comes from. And we're choosing 5 girls from 12 girls, so 12C5, if you were to use that formula and expand this out completely, you'll get, well, expand this out completely and then do some cancellation, you get 792. So there's 792 ways that we can choose 5 girls and 0 boys from the 12 girls in the class. And the probability that a committee of 5 chosen at random from the class consists of only girls would be this. The total number of committees of 5 would be that 26,334 that we talked about earlier. And then from part C, there are 792 ways to choose 5 girls and 0 boys. That probability would be 792 divided by 26,334, which will be as a decimal 0.030. So the probability there will be 0.030. Okay, so that will conclude that particular section on permutations and combinations that are used in probability.